Oftentimes when I'm teaching a different mathematical concept or we're looking at a certain type of function, students ask why we're studying this particular type of function and if there are any real-world examples of things that are modeled off of that type of function. And unfortunately, right now, we do have a very good example of something that is modeled off of an exponential function, and that is the spread of the coronavirus. I know that this might be the last thing that some of you want to talk about, but I think it's very appropriate that we're studying exponential functions to look at this, and so I want to use this video to take a look at a particular graph. So this is a graph, and this is not the number of cases, but rather the number of deaths related to COVID in New York State. So these are COVID deaths in New York State, specifically from March 11th through March 31st of 2020. Now, the reason that I looked at deaths instead of the number of cases is because I actually was in New York at this time. Actually, I arrived in New York, I think, on the 28th of March. And at this point, it was almost impossible to get a COVID test, even if you were showing symptoms, unless your symptoms were extreme. So it's widely believed that a lot of the data at this time for the number of positive tests is undercounting people because so many people who likely had it weren't tested. However, the deaths are probably more accurate, so that's the graph that we're going to look at. And here you can see the first death actually was on March 11th. There was one death there and there were 0 deaths before then. And as we move through time, for the first half of this time period, there really wasn't that much of an increase. It increased little by little, but then there got to be a point around here where it starts increasing very, very quickly. And I want to bring up a couple of these data points in particular. So if we look at March 31st, the number of deaths cumulatively by then was 3,244. So this, here, let me write here. This point has a height of 3,244. And then if we look at the day before that, it is 2,585. So in one day, the number of deaths rose, I think, almost 600 or 700. I believe between 600 and 700 deaths in that day. So in the very beginning, we had 1 death, we went up to 2 deaths. The deaths were in the single digits here per day. But after just a couple of weeks, we're to the point where there's over 600 deaths in a single day. So even though this doesn't look that steep, it's because these scales are quite different. This covers about 20 days, and the rise here is well over 3,000. So if we were to make the scales so that each of them were the same, this graph would be going up well outside the range of my iPad. So it's important to recognize that this is a situation where things really didn't happen very quickly at first, but eventually we get to the point where it's growing out of control. And this graph eventually ends up getting bigger and bigger and bigger and bigger, but then it starts to level out, and eventually it looks something like this. This is not to scale, this is just a sketch. And the reason that it doesn't continue to grow exponentially is because we started closing businesses and restaurants, and people were asked to shelter in place, and people started wearing face masks and not going out unless there was something essential they needed to do. And so oftentimes if we have a virus or bacteria or something like that, the spread is exponential, but it's usually not exponential forever. Usually there's something that prevents it from growing out of control. In this case, it was because people started to act more responsibly, because we were learning more about how to protect ourselves from the virus. But even if that hadn't happened, eventually we would get to a point where there are no more humans and the graph cannot grow exponentially forever. So in general, exponential functions can model certain things, but usually there's a point where some other variable kicks in and it no longer ends up being exponential. Now, another situation where we have exponential growth, and this is a happier situation generally, is with compound interest in bank accounts. And this is something that we're going to look at in a few classes from now. So we will see a happier example of an exponential function, but I just wanted to take this opportunity to bring up a real-life situation that has at least indirectly, if not directly, affected all of us, and see just how important it is to be able to understand the math behind what's going on.